Welcome again to the last chapter on, or the last class on the moment of inertia. Let's solve few simple problems. Let's suppose we have a rectangle and we are given that the dimensions of the rectangle are its height is, say for example, given to us, and its breadth is also given to us. Let's say the breadth of the rectangle is b and the height of the rectangle is, say for example, h. We know, as far as the centroid of the rectangle is concerned, the centroid of the rectangle lies at its geometrical center. So let's suppose this is the centroid of this rectangle. This point represents the centroid of the rectangle. Therefore, we can define this axis to be our centroidal x-axis, and we can define this axis to be our centroidal y-axis. Okay. Now, apart from centroidal x and y-axis, let's define this to be our x-axis, and let's say this is our y-axis, such that we know, as far as the distance is concerned, as far as since we are calling this to be our centroid, we know centroid of the rectangle lies at the geometrical center, and let's say the distance between then between these two axes, or I have not drawn, let's read up this, the distance between, let's call this is our centroidal x-axis. I will write this as x prime. This is our centroidal y-axis. Let's call this as y prime. And we have, this is our y-axis, centroidal y-axis. Let's call this as y prime. The distance then between this x-axis and the centroidal x-axis will be equal to, this distance will be then equal to half of the height. The reason is because this lies at the geometrical center. This total distance is h, therefore this distance will be h by 2. Similarly, as far as the distance between the corresponding y-axis, centroidal y-axis and y-axis is concerned, that will be equal to b by 2. Now the question is, first of all, let's calculate the moment of inertia about the centroidal x-axis. That is, we have to calculate the moment of inertia of this area about the centroidal x-axis, that is ix prime, x prime. Okay, so in order to do that, we know the definition is ix prime is equal to integral of y square dA. This is the basic definition that we are given. As far as this y is concerned, this y is the y coordinate of the small area element dA from the axis from where we are measuring the moment of inertia. We are measuring the moment of inertia, okay, from this x-axis. So first of all, we have to locate our area element. So let's draw our area element. Since we have to find the moment of inertia about the y-axis, so we'll be translating along the y-axis. So our area element should be essentially like this. Let's say this is our area element. Okay, let's call this to be our small area element. Let's say this is our area element, and we say that the area of the small area element will be, this distance is, this is equal to b, this is equal to b, and the distance along y-axis is very small. Let's call this as dy. Therefore, as far as the dA is concerned, our dA will be equal to b times dy. dA is equal to b dy. Now we have to see, this is our area element dA. This area element is also in the form of a rectangle. Its centroid will be at its geometrical center, and let's suppose its centroid is at a distance y from this x prime axis. Therefore, we can write this is equal to integral the y coordinate of the centroid of the area element as measured from x prime is y, that is y square, and dA, as far as dA is concerned, that's equal to b dy. Okay, and since now the variable of integration is y, the area element has to traverse from this end to this end. Okay, it has to traverse to this entire area. So if we look at, since we are measuring, we are calculating the moment of inertia about this centroidal x-axis. So this is our origin. Okay, so from the origin, this is our x is equal to 0 or and y equal to 0. From this origin we have to go to this distance. Our area element should go to this distance, as well as it should go to this distance. Okay, as far as this limit is concerned, as measured from this point, this will be equal, this is in the negative direction of y-axis, and this is will be equal to minus h by 2. Okay, this coordinate is minus h by 2 as measured from this axis, centroidal x-axis, and this coordinate will be plus h by 2. Okay, so our limits of integration will be minus h by 2. Our y has to go from minus h by 2 to plus h by 2 plus h by 2. That is equal to integral b will come out of integration. This is integral y square dA. That is equal to y cube by 3, going from minus h by 2 to plus h by 2. Okay, which is equal to b by 3, which is equal to b by 3. Then this is y cube. This is h cube by 8 minus, this is h minus, this will be h cube by 8, but this is minus, minus will become plus. This will be again h cube by 8. That will be equal twice h cube by 8, that is equal b by 3 multiplied by h cube by 4. That is equal to 1 by 12 bh cube. 1 by 12 bh cube. So it means, therefore, as far as the moment of inertia of a rectangle, the moment of inertia of a rectangle about the centroidal x-axis is concerned, the moment of inertia of the rectangle about centroidal x-axis is concerned, that's equal to 1 by 12 b h cube. Okay, this is what we have calculated now. Now, if we are asked, calculate the moment of inertia about this x-axis, that is, if we have to calculate the moment of inertia, if we are asked now to calculate the moment of inertia about the x-axis, what we will do, the moment of inertia about the x-axis will be equal, the moment of inertia about x-axis will be equal, using the parallel axis theorem, will be equal, moment of inertia about this x-axis will be equal to moment of inertia about ix prime, centroidal x-axis, moment of inertia about the centroidal x-axis, plus total area times the square of distance between the two axes, x-axis and x prime axis. I will write this as dx square. That's what we have done. That is equal, ix prime is equal 1 by 12 bh cube, 1 by 12 bh cube. Area of the rectangle is equal to b multiplied by h, okay, total area, multiplied by the square of the distance between these two axes, that is h by 2 square, that is h square by 4. Okay, that is equal to bh cube by 12 plus bh cube by 4, which is equal to, if we perform, uh, that will be uh, 4 by 12 bh cube, that is equal to 1 by 3 bh cube, that is 1 by 3 bh cube. So this is very important. This we have obtained from by using the parallel axis theorem. So for a rectangle, the moment of inertia about the centroidal x-axis is equal 1 by 12 bh cube. Okay, and the moment of inertia about an axis which is parallel to the centroidal x-axis and passing through one of its side, it's equal to 1 by 3 bh cube. In the same way, we can calculate the moment of inertia about the y-axis. If we are asked to calculate now the moment of inertia about the centroidal y-axis, this I am leaving as an exercise to students that they can themselves calculate the moment of inertia about the centroidal y-axis, ixy prime. That will be equal the moment of inertia about the centroidal y-axis, the moment of inertia about this axis, centroidal y-axis, will be equal to 1 by 12. Now, in order to find the moment of inertia about the centroidal y-axis, okay, so the formula will be, we have to take an area element now in this direction, okay, and make the area element traverse from this direction to this direction. That will be from minus b by 2 to plus b by 2. Okay, the formula will be 1 by 12 h b cube. This will be the formula. Moment of inertia about the centroidal y-axis, and the moment of inertia about the y-axis passing through one of the side will be equal to 1 by 3 HBQ. You can, I am leaving this as an exercise to students to find the moment of inertia about the centroidal y-axis and this y-axis in the same way as we have found the moment of inertia about x-axis, centroidal x-axis and x. Let's again use a rectangle. Let's suppose we again have a rectangle, and this is our centroid. Let's call this as our centroidal x-axis, and let's suppose this is our centroidal y-axis, and this is simply our x-axis passing through one of the side, and this is again our, okay, this is our centroidal x-axis. We call this as x prime, this is y prime, this is y-axis, this is x-axis, this is centroid, this is the origin. Okay, now what we will do, let's calculate the product of inertia again. Let's now calculate the product of inertia Ixy. If we are asked to calculate the product of inertia Ixy about the centroidal x and centroidal y axis, okay, we have to calculate the product of inertia about the centroidal x, and this is our centroidal x axis, this is centroidal y axis. For that purpose, what we will do, we know the product of inertia about the centroidal y axis is concerned, it's equal x prime y prime or xy x into y dA. That is, from the definition, we have to select a small area element. We have to select a small area element. Let's suppose its area is dA. Let's suppose the centroid of the small area is at a distance y prime from the centroidal x-axis and is at a distance x prime from the centroidal y-axis. Okay, so as far as this element is concerned, this is our area element. Okay, so we can write in our formula, this is integral x coordinate of the centroid of the small area element as measured from x prime axis. We write this as, this is x prime y prime dA. Okay, now look at this area element. This area element, we have to integrate this area element over the entire area. Okay, over the entire area of this rectangle. If you see this area element here, okay, its x coordinate here is positive and its y coordinate is positive, but we have to make this area element traverse the entire area to solve this integral. Okay, now corresponding to this area element on this side, we'll be having one more area element on this side whose x coordinate from the y-axis will be x prime, but it will be negative, and y prime of the centroid will be positive. We call that as y prime. Okay, we by the definition of integration, we have to divide this area into infinite number of area elements. Okay, because integration is simply the simplest way of performing. It's at the end of the day, the integration is simply the addition. Okay, so as far as this xy dA is concerned, once we are using this xy dA for this element, okay, so we know x coordinate of the centroid of the small area element, we know y coordinate of the centroid of the small area element, we know its area is very, very small, let that be dA. We have now to perform the integration. We have to integrate it over the entire area. When this area on its left hand side will have one more area, we will have one more area element dA. Okay, or we suppose, as you integrate this area element has to traverse through the entire space available, entire area of the plane. Okay, as this area element reaches here, by the process of integration, what happens? Your x coordinate becomes negative, your y coordinate is positive. Okay, so it means the product of inertia of this area element is being cancelled by the product of inertia of this area element. Okay, because these two area elements are symmetric to each other. In the same way, as this area element will reach here, somewhere here, okay, its y coordinate will be now negative, its x coordinate is also negative, its x coordinate is negative, y coordinate is negative, and when this area element will reach to a symmetrical position here in this direction, its x coordinate becomes positive and its y coordinate becomes positive, okay. But this position of the area element and this position, its x coordinate is same, y coordinate is same as x coordinate and y coordinate of this area element, but their directions are opposite. So by the process of integration, this product of inertia of this element will cancel by the product of inertia of this element, okay. The area element on this side will have a negative symmetry, okay, will have a symmetric on the left hand side, but that will be negative. Same is here, same is here. The total product of inertia therefore will come out to be equal 0, okay. Therefore we say this is a general theorem. The product of inertia about the centroidal axis is always equal to 0. The product of inertia about the centroidal axis is always equal to 0. You should always remember this. The product of inertia of an area about the centroidal axis is always and always equal to 0. So this was our centroidal x-axis. This was our centroidal x-axis, and we were trying to calculate the moment of inertia about the centroidal x-axis. Okay, this was the moment of inertia we were trying to calculate. We are trying to calculate the moment of inertia about the centroidal x-axis. Okay, what about, sorry, the product of inertia we were trying to calculate about the centroidal x-axis and centroidal y-axis. Centroidal in centroidal xy system, the product of inertia is 0. What will be the product of inertia about any other system like this xy system? Okay, the product of inertia about xy system is equal to the product of inertia about the centroidal xy system plus area times the product of the distances between the two. This distance is equal to h by 2, and this distance is equal to, b by 2. Okay, this will be a into h by 2 multiplied by b by 2 by the parallel axis theorem for the product of inertia. This term is equal to 0. The product of inertia about the centroidal xy system is 0. Therefore, Ixy becomes equal to a into h into b divided by 4. As far as h into b is concerned, that is also equal to area. That is therefore equal to a into b becomes a square by 4. That is equal to a by 2 whole square. Okay, this is the product of inertia of a rectangle about the xy system passing through its parallel to its sides. But as far as the product of inertia about the centroidal xy system is concerned, that is equal to 0. Thank you.